So here's something to think about as you settle in tonight. Right now, somewhere in the world, there is a mathematician staring at a piece of paper. Maybe it's a chalkboard, maybe it's a tablet screen, but it doesn't matter, because what they're really staring at is a question. A question that might have been asked 300 years ago, or 2,000 years ago, or maybe just 50 years ago, but the point is, nobody has answered it yet. Not for lack of trying. Some of the greatest minds in human history have spent years, decades, entire lifetimes chasing these problems, and the problems just sit there, patient and quiet, waiting. And that's what we're going to talk about tonight. Unsolved problems in mathematics. The ones that have resisted every attack, every clever trick, every flash of genius thrown at them. We're going to go slowly because there's no rush, and because these ideas deserve a little breathing room. Some of them are deceptively simple to state, so simple that you might hear one and think, well, that can't be that hard. And then you'll learn that people have been trying to prove it for centuries, and you'll feel that wonderful vertigo of realizing how deep the rabbit hole goes. But before we get to any specific problem, let's just sit with this idea for a moment. What does it even mean for a math problem to be unsolved? It's not like an engineering challenge where you're waiting for better materials or faster computers, although sometimes those help. It's more fundamental than that. An unsolved math problem is a statement about the universe of numbers, or shapes, or patterns that we believe to be true, or at least suspect to be true, but cannot yet prove with absolute logical certainty. And in mathematics, proof is everything. You can check a billion examples and find that something works every single time, and a mathematician will nod politely and say, "That's very nice," but it's not a proof, because maybe the 1,000,001st example breaks the pattern. Maybe it doesn't. But until you can show why it must always work, or why it must sometimes fail, the question remains open. There's something almost philosophical about that, isn't there? This insistence on certainty. In most of life, we're comfortable with pretty sure. In engineering, you build in safety factors. In science, you work with confidence intervals. But mathematics demands something absolute. Either you can prove it, or you can't. And if you can't, the problem stays unsolved, no matter how obvious the answer seems. Now, the story of unsolved problems is really the story of mathematics itself. So let's start where mathematics started, or at least where the written record lets us pick up the thread. And that means we're going back a long way, to ancient Mesopotamia, to the banks of the Tigris and Euphrates rivers, something like 4,000 years ago. The Babylonians were remarkable mathematicians. We know this because they wrote on clay tablets, and clay, unlike paper, survives millennia. Thousands of these tablets have been found, and they show a civilization that understood quadratic equations, that could calculate square roots to impressive accuracy, that had tables of what we'd now call Pythagorean triples, sets of whole numbers where the squares of two of them add up to the square of the third, 3, 4, 5, 5, 12, 13. They knew these long before Pythagoras was born. But here's what's interesting about the Babylonians for our purposes tonight. They were practical mathematicians. They solved problems because they needed to measure fields, to calculate volumes of grain, to track the movements of planets for their calendar. They didn't, as far as we can tell, ask the kind of open-ended theoretical questions that lead to unsolved problems. They weren't trying to prove that something was always true for every possible case. they were trying to get answers, specific answers to specific questions, and they were very good at it. The shift, the moment when mathematics went from being a tool for solving practical problems to being a universe of ideas you could explore for their own sake. That happened in Greece. And the person most associated with that shift, although it certainly wasn't just one person, is Pythagoras, who lived around 500 BCE. Now, Pythagoras is one of those figures where the legend has almost completely swallowed the history. He led what was essentially a mathematical cult. His followers, the Pythagoreans, believed that numbers were the fundamental reality of the universe. Not just useful for describing reality, they were reality. Whole numbers and their ratios, what we call rational numbers, were the building blocks of everything. It was a beautiful, elegant worldview. And then it broke. The story goes, and this is one of those stories where the exact details are debated, but the core of it is well established, that a Pythagorean named Hippasus discovered that the square root of 2 cannot be expressed as a ratio of whole numbers. It's irrational. If you draw a square with sides of length 1, the diagonal has a length that cannot be written as any fraction, no matter how complicated. It goes on forever without repeating. 1.41421356 and on, never settling into a pattern. This was devastating to the Pythagorean worldview. If numbers were supposed to be the foundation of everything, and the most basic geometric shape, a square, produced a number that didn't fit into their system, then something was deeply wrong. Legend has it that Hippasus was drowned at sea for revealing this discovery, though that's probably more myth than history. But the discovery itself was real, and it was the first great crisis in mathematics. The first time that a seemingly simple question, "Can you express this length as a fraction?" turned out to have a shocking answer. And in a way, that's the template for every unsolved problem that came after. You start with something that seems straightforward. You pull on the thread, and the whole tapestry starts to unravel in ways nobody expected. The Greeks, to their enormous credit, didn't run from this crisis. They leaned into it, and the person who really showed the world what rigorous mathematical proof could look like was Euclid, working in Alexandria around 300 BCE. His Elements is one of the most influential books ever written, not just in mathematics, but in all of human thought. What Euclid did was start with a small set of axioms, basic assumptions so simple they seemed self-evident, and then build an entire edifice of geometry through pure logical deduction. One theorem leading to the next, each one proven beyond any possible doubt, given the axioms. And tucked inside the elements are some genuinely beautiful results that touch on questions we're still thinking about today. Here's one. Euclid proved that there are infinitely many prime numbers. Think about what that means. Prime numbers, numbers divisible only by 1 and themselves, 2, 3, 5, 7, 11, 13, and so on. They never run out. No matter how far you go along the number line, you will always find another prime. Euclid proved this, and his proof is still taught in every introductory number theory course in the world, and it's still considered one of the most elegant arguments in all of mathematics. Here's how it works, roughly. Suppose, just for the sake of argument, that there are only finitely many primes. You could list them all. Fine. Now multiply all of them together and add 1. The number you get is either prime itself or it's divisible by some prime. but it can't be divisible by any of the primes on your list, because dividing by any of them leaves a remainder of 1. So either it's a new prime you missed, or it has a prime factor you missed. Either way, your list was incomplete. Contradiction. There must be infinitely many primes. That's it. That's the whole proof. It's over 2,000 years old and it's still perfect. Makes you wonder what Euclid would think if he knew people were still talking about it. But here's the thing. Knowing that there are infinitely many primes immediately opens up new questions. How are they distributed? Is there a pattern? If you look at the primes up to 100, they seem to thin out. They get less frequent as numbers get larger. But they never stop entirely. So what's the rule? How exactly do they thin out? This is one of those questions that sounds simple and turns out to be extraordinarily deep. The prime numbers are, in some sense, the atoms of arithmetic. Every whole number bigger than 1 is either prime or can be broken down into primes in exactly one way. 6 is 2 times 3. 30 is 2 times 3 times 5. This is called the fundamental theorem of arithmetic, and it means that if you understand the primes, you understand the building blocks of all numbers. But the primes themselves seem to follow no neat pattern. They feel almost random, scattered along the number line, like stones dropped by some capricious hand. And yet they're not random. They're completely determined. There's nothing uncertain about whether a given number is prime. It either is or it isn't. The apparent randomness is just our inability to see the pattern, if there even is one in the way we'd normally think about patterns. The Greeks noticed something else about primes that's charming and still unresolved. Sometimes primes come in pairs, separated by just 2, 3 and 5, 5 and 7, 11 and 13, 17 and 19, 29 and 31. These are called twin primes, and they pop up throughout the number line. The question, and this is an unsolved problem that's been around for well over 2,000 years, is whether there are infinitely many twin prime pairs or whether at some point they stop. Just let that settle for a second. We know there are infinitely many primes. Euclid proved that. But are there infinitely many pairs of primes that are just 2 apart? Nobody knows. As of right now, the largest known twin prime pair has hundreds of thousands of digits. Computers have searched incredibly far along the number line and keep finding them. Every mathematician you ask will tell you they believe the answer is yes, there are infinitely many. But believing and proving are very different things in mathematics, and no one has managed a proof. There has been progress, though, and it's a wonderful story. In 2013, a relatively unknown mathematician named Yitang Zhang, who had struggled for years in academia and had even worked at a Subway sandwich shop at one point, published a paper that stunned the mathematical world. He proved that there are infinitely many pairs of primes that differ by at most 70 million. Now, 70 million is a lot bigger than 2, so this wasn't the twin prime conjecture, but it was the first time anyone had proven that prime pairs with any fixed gap appear infinitely often. Before Zhang, mathematicians couldn't even prove that for a gap of 70 million, let alone 2. And then something beautiful happened. The mathematical community, inspired by Zhang's breakthrough, launched a collaborative effort to shrink that gap. Within months, the bound dropped from 70 million to thousands, then to hundreds. A massive online collaboration called the Polymath Project, organized partly by the field's medalist Terence Tao, pushed the bound down to 246. As of now, that's roughly where it stands. We know there are infinitely many prime pairs, with a gap of at most 246. But getting from 246 all the way down to 2, that last stretch, remains out of reach. It might require entirely new ideas, entirely new mathematics that hasn't been invented yet. And that's one of the things I find most compelling about unsolved problems. Sometimes you can see the destination. You can practically point at it. But the bridge to get there doesn't exist yet, and building it might take a generation, or a century, or it might happen next Tuesday when someone has the right idea in the shower. The twin prime conjecture is part of a much larger web of questions about prime numbers, and many of those questions trace back to one of the most important and most mysterious unsolved problems in all of mathematics. You've probably heard of it, even if you're not sure exactly what it says. It's called the Riemann Hypothesis, and we're going to spend some real time with it because it deserves that. But to understand where it came from, we need to fast forward from ancient Greece to 18th century Europe, to a time when mathematics was exploding with new ideas, and one question about prime numbers was starting to obsess some of the greatest minds of the age. The person who set the stage was Leonhard Euler, a Swiss mathematician who worked in the 1700s and who was, by any reasonable measure, one of the most productive mathematicians who ever lived. Euler was prolific to a degree that's almost hard to believe. He published over 800 papers and books. He continued working even after going blind in both eyes, dictating his results to assistants. He made fundamental contributions to calculus, number theory, graph theory, mechanics, optics, astronomy. The list goes on and on. There's a joke among mathematicians that things are named after the first person to discover them after Euler, because Euler discovered so many things first. And one of the things Euler noticed was a deep and surprising connection between prime numbers and something that seems completely unrelated: infinite sums. He showed that if you take the sum of 1 over n squared for all whole numbers n from 1 to infinity, so 1 over 1 plus 1 over 4 plus 1 over 9 plus 1 over 16, and so on, this sum converges to exactly pi squared over 6. Pi, the circle number, showing up in a sum that has absolutely nothing to do with circles, at least not obviously. That result alone is stunning, and Euler was the first to prove it. But Euler went further. He connected these kinds of infinite sums directly to prime numbers through a beautiful identity, and that identity would eventually become the seed from which the Riemann hypothesis grew. About a century after Euler, a young German mathematician named Bernhard Riemann would pick up that thread and follow it into territory so strange and so deep that we're still trying to map it today. Riemann was quiet, often sickly, and deeply private. But in 1859 he published a short paper, just 8 pages, that contained one of the most consequential conjectures in the history of human thought. And to understand what he proposed and why it matters so much, we need to talk about what happens when you extend Euler's ideas into the complex plane, into a world where numbers have not just size, but direction. That's really the key idea here, and it's worth sitting with for a moment, because it's one of those concepts that sounds intimidating, but is actually quite beautiful once you let it settle in. So you know how regular numbers, the ones you use every day, live on a line? You can picture it. 0 in the middle, positive numbers stretching off to the right, negative numbers stretching off to the left. Every number you've ever used to measure something, count something, pay for something, it sits somewhere on that line, and that line is great. It's done incredible work for us for thousands of years. But mathematicians, being the restless explorers they are, eventually asked a question that seems almost absurd. What if numbers didn't just live on a line? What if they lived on a plane? And that's exactly what complex numbers give you. A complex number has two parts. There's the regular part, the part that sits on that familiar number line, and then there's a second part, multiplied by this strange quantity called I, which is defined as the square root of -1. Now, if that makes you furrow your brow a little, you're in good company. When complex numbers were first introduced, mathematicians themselves were deeply suspicious of them. They called them imaginary numbers, and that name stuck, which is a bit unfortunate because it makes them sound made up, like they're less real than real numbers. But here's the thing, they're not made up any more than negative numbers are made up, or fractions, or zero. They're a tool, an extension, and they turn out to be extraordinarily powerful. The way to picture it is this. Instead of a number line, you have a number plane. The horizontal axis is your regular real numbers. The vertical axis is the imaginary part. So every point on this plane represents a complex number. It has a position left to right, which tells you its real part, and a position up or down, which tells you its imaginary part. A number like 3 plus 2, I would sit 3 units to the right and 2 units up. Simple as that. And this plane, this flat, two-dimensional space of numbers, is what mathematicians call the complex plane. Now, why does this matter for prime numbers? Why does this matter for Riemann? Because Euler's beautiful infinite sums, the ones that connected primes to infinite series, were defined using real numbers. You'd plug in a real number, say 2, and you'd get a value out, like pi squared over 6. But Riemann asked, what happens if I plug in a complex number instead? What if I let the input to Euler's function wander off that real number line and roam freely across the entire complex plane? And this is where Riemann's genius really shows. The function Euler had been studying, the one where you sum up 1 over n to the power of s, for n running from 1 to infinity, that function only makes sense, only converges, when the real part of s is greater than 1. If you try to plug in s equals 1, for instance, you get the harmonic series, which diverges. It blows up to infinity. So there's this whole vast territory of the complex plane where the original sum simply doesn't work. It's undefined. It's like trying to use a map that only covers one small corner of the landscape. But Riemann found a way to extend the map. Through a process called analytic continuation. And don't worry too much about the technical details here, just the idea. He showed that there's exactly one smooth, natural way to extend this function so that it's defined almost everywhere on the complex plane. The extended function agrees with Euler's original sum wherever that sum works, but it also gives you values in places the original sum couldn't reach. It's like discovering that the road you've been driving on actually continues through a tunnel and out the other side into a whole new country. Same road, same direction, but now you can go so much further. This extended function is what we call the Riemann zeta function, and it's one of the most studied objects in all of mathematics. Entire careers have been built around understanding its properties, and the reason, the deep, fundamental reason it matters, is that the zeta function encodes information about prime numbers in its structure, specifically in its zeros. Let's talk about what that means. A zero of a function is just an input that makes the function output 0. Simple enough, right? If you think of a basic parabola, y equals x squared minus 4, that function has zeros at x equals 2 and x equals -2. Because those are the inputs that make y equals 0. The Riemann zeta function also has zeros, inputs in the complex plane where the function's value is exactly zero. And some of these zeros are easy to find. The function equals 0 at -2, -4, -6, and so on, all the negative even integers. These are called the trivial zeros, and they're well understood. They're not particularly mysterious. But then there are the other zeros, the non-trivial ones. These are the zeros that live inside a vertical strip of the complex plane, specifically the strip where the real part of the input is between 0 and 1. This strip is called the critical strip, and somewhere inside it, the non-trivial zeros are hiding. And here's what Riemann conjectured in that short, remarkable 1859 paper. Every single non-trivial zero of the zeta function has a real part of exactly 1/2. Every one. They all sit on a single vertical line, the line where the real part equals 1/2, running straight up and down through the complex plane. That line is called the critical line. That's the Riemann hypothesis. That's it. All non-trivial zeros lie on the critical line. It's a statement you can write down in one sentence. And yet, no one has been able to prove it in over 160 years. Now, you might be thinking, okay, so some function has zeros on a line. Why should anyone care? And this is where it gets really interesting, because the location of those zeros is directly, intimately connected to how prime numbers are distributed among all the other numbers. There's a formula, an explicit formula, worked out in detail by later mathematicians building on Riemann's ideas, that expresses the exact count of primes up to any given number in terms of the zeros of the zeta function. Each zero contributes a wave-like correction to the estimate. If all the zeros are on the critical line, those waves are as well behaved as possible, and the primes are distributed as regularly as they can be. If even one zero is off the line, if even one is lurking somewhere else in the critical strip, it would mean there's an unexpected irregularity in the primes, a wobble in their distribution that we haven't accounted for. Think of it like this. Imagine you're listening to an orchestra, and the primes are the melody. The zeros of the zeta function are like the individual instruments contributing to that melody. The Riemann hypothesis says all those instruments are perfectly in tune. They're all playing at the right frequency. If one instrument is slightly off, the melody develops a strange dissonance, an unexpected pattern that shouldn't be there. Proving the Riemann hypothesis would be like proving that the orchestra of primes is perfectly tuned, that their distribution has exactly the kind of regularity that mathematicians have long suspected, but never been able to confirm. And people have checked. Oh, they've checked extensively. As of recent computations, over 10 trillion non-trivial zeros have been calculated, and every single one of them sits right on the critical line, exactly where Riemann said they should be. 10 trillion zeros, all in a row, all perfectly placed. And yet, that's not a proof. Remember what we talked about earlier, how in mathematics, 1 billion examples aren't enough? How you need absolute certainty, covering every case forever. There are infinitely many non-trivial zeros, and checking 10 trillion of them, as impressive as that computational feat is, doesn't rule out the possibility that zero number 10 trillion and 1 might be the exception. Riemann himself didn't live long enough to make much more progress on the problem. He died in 1866, just 7 years after publishing that paper, at the age of 39. Tuberculosis. He spent his final months in Italy, seeking warmer air for his failing lungs. It's one of those heartbreaking what-ifs of mathematical history. What might Riemann have accomplished with another 20 or 30 years? The paper itself was almost offhand in how it presented the hypothesis. Riemann mentioned it as something he considered very likely, but didn't pursue a proof. He had other things on his mind, other results to present. He probably had no idea that this particular conjecture would become the central unsolved problem of mathematics. After Riemann's death, other mathematicians picked up the trail. One of the most important was Jacques Hadamard, a French mathematician who, in 1896, along with the Belgian Charles de la Vallée-Poussin, independently proved the prime number theorem, which gives the approximate density of primes among the integers, and their proofs relied on properties of the zeta function. They didn't prove the Riemann hypothesis, but they showed that no zeros exist on the edge of the critical strip. That is, no zeros with real part equal to 0 or 1. That was enough to establish the prime number theorem. But the full hypothesis that everything collapses to the line at 1/2 remained open. In 1914, the great English mathematician G.H. Hardy proved that infinitely many zeros do lie on the critical line. That was a major step. It showed the critical line isn't just a hopeful guess. It really is where zeros accumulate. But infinitely many on the line doesn't mean all of them are on the line. There could still be rogues, outliers, zeros sitting slightly to the left or right of 1/2, hiding among the infinitely many well-behaved ones. Hardy himself had a fascinating relationship with the problem. He was one of the foremost analytic number theorists of his era, working at Cambridge, and he had a famous collaboration with the Indian mathematical genius Srinivasa Ramanujan. But that's a story we'll come to a bit later. Hardy was known for his pure love of mathematics for its own sake, and he once listed the Riemann hypothesis as one of the things he'd most like to see resolved. He also reportedly used it as a kind of insurance policy. The story goes that when crossing the English Channel by boat in rough weather, he would send a postcard to a colleague claiming he'd proved the Riemann hypothesis, figuring that God wouldn't let him drown and thereby grant him undeserved glory. Whether that story is true or apocryphal, it captures something about how mathematicians relate to this problem, with a mixture of reverence, obsession, and dark humor. The Riemann hypothesis sits at number 1 on most lists of the greatest unsolved problems in mathematics. It's one of the 7 Millennium Prize problems designated by the Clay Mathematics Institute in the year 2000, each carrying a prize of $1 million. And of those 7, many mathematicians would tell you, the Riemann hypothesis is the deepest, the most consequential, the one whose resolution would send the longest shock waves through the mathematical landscape. Hundreds of theorems in number theory, in analysis, in mathematical physics, begin with the phrase, assuming the Riemann hypothesis. They're conditional results, true if the hypothesis holds, uncertain if it doesn't. Proving it would instantly promote all of those conditional theorems to unconditional truths. Disproving it, finding even 1 zero off the critical line, would be equally seismic, forcing mathematicians to rethink fundamental assumptions about the structure of the primes. And here's something lovely to think about as you settle deeper into wherever you are right now. The primes, those stubborn, indivisible numbers, have been studied for well over 2,000 years. The ancient Greeks knew they were infinite. Euler connected them to infinite sums. Riemann connected those sums to the complex plane and found that the secret to understanding primes might live in the zeros of a single, elegant function. And we've checked trillions of those zeros, and they all line up perfectly on that critical line. But we still can't prove it must always be so. The pattern holds beautifully, relentlessly, but the proof remains just out of reach, like a door that you can see through, but can't quite open. Now, the Riemann hypothesis is about the distribution of primes in a very specific analytic sense. But there are other unsolved problems about primes that are much easier to state, problems that sound so simple you might think a bright teenager could solve them over a weekend. And one of the oldest, most tantalizing of these, one we touched on earlier when we talked about twin primes, has a cousin that's even more famous, even more maddening in its simplicity. It involves not the gaps between primes, but the idea that every even number can be built from them. It's called the Goldbach Conjecture, and it starts with a letter written in 1742. Christian Goldbach, a Prussian mathematician living in Russia, working as a tutor to the young Tsar Peter II, wrote a letter to Leonhard Euler. Yes, the same Euler we've already met, the one who figured out that the sum of the reciprocals of the squares equals pi squared over 6. Goldbach and Euler had been corresponding for years, trading mathematical ideas back and forth the way people today might trade links to articles. And in this particular letter, dated June 7th, 1742, Goldbach scribbled a conjecture in the margin. His original phrasing was a little different from how we state it today. He was working with a convention where 1 was considered a prime number, which we no longer do. But once you clean up the language and translate it into modern terms, the claim is breathtakingly simple. Every even integer greater than 2 can be expressed as the sum of 2 primes. That's it. That's the whole thing. Take any even number. Pick one, any one you like. 6, that's 3 plus 3. 8, 5 plus 3. 10, 7 plus 3, or 5 plus 5. 20, 13 plus 7. 100, 97 plus 3. A million? You can find a pair. A trillion? Same. Every even number anyone has ever checked, and computers have verified this up to numbers with 18 digits, numbers in the quintillions, can be written as the sum of 2 primes. Every single one. No exceptions. Not one counterexample in nearly 3 centuries of looking. And yet, nobody can prove it. Let that sit for a moment. The statement is so simple that a child can understand it. You could explain it to someone who's never taken a math class. 2 plus 2 equals 4, 3 plus 3 equals 6, 5 plus 7 equals 12. You get the idea immediately. But proving that this must always work, for every even number stretching out to infinity, that every single one without exception can be split into 2 prime pieces, that has defeated every mathematician who has ever tried for over 280 years. Euler, to his credit, responded to Goldbach's letter with interest. He considered the conjecture likely to be true, but couldn't prove it. And remember, this is Euler we're talking about, arguably the most prolific mathematician in history, a man who published more mathematical papers than anyone before or since, who kept working even after he went blind, dictating equations to his assistants from memory. If Euler couldn't crack it, that tells you something about the depth of the problem. Now, here's what makes the Goldbach conjecture so frustrating and honestly so beautiful from a mathematical standpoint. Primes are defined by multiplication. A prime is a number that can't be broken into smaller factors. But the Goldbach conjecture is about addition. It's asking whether these multiplicatively defined objects, the primes, have a particular additive property, and that boundary between multiplication and addition is one of the deepest, most treacherous frontiers in all of number theory. It's the place where our tools tend to break down. We have incredible machinery for understanding how primes multiply together. That's basically what the Riemann zeta function is about. But understanding how primes add up, how they combine through simple addition, is a fundamentally different kind of question, and it's much, much harder than it looks. Think of it this way. Imagine you have a bag of oddly shaped stones. Those are your primes. You know a lot about how those stones stack vertically, how they build towers, how they factor into layers. But someone asks you, can you always lay exactly two of those stones side by side on a table and have their combined width equal any even measurement you choose? You're being asked about a completely different property of the stones, their widths, not their stacking behavior. And all your expertise about towers doesn't directly help. So what progress has actually been made? Well, the story of partial results on the Goldbach Conjecture is a story of mathematicians chipping away at the edges, unable to reach the center, but getting closer in fascinating ways. And the biggest breakthrough came from an unlikely direction, from a man working in near isolation during one of the most turbulent periods of the 20th century. In 1937, a Soviet mathematician named Ivan Vinogradov proved something remarkable. He couldn't prove the Goldbach conjecture itself, the statement about two primes, but he proved what's called the weak Goldbach conjecture, or sometimes the odd Goldbach conjecture. This is the claim that every odd integer greater than 5 can be expressed as the sum of 3 primes, not 2, 3. It sounds like a lesser result, and in some sense it is, but the techniques Vinogradov developed to prove it were extraordinary. He used what are called exponential sums, intricate, delicate calculations involving waves of complex numbers, not entirely unlike the wave-like behavior we talked about with the Riemann zeta function. Vinogradov showed that for sufficiently large odd numbers, the result holds. The catch, and there's always a catch, was that sufficiently large meant really absurdly large. The bound was so enormous that you couldn't just check the remaining cases by computer. The gap between the smallest number his proof covered and the numbers you could feasibly check was vast, and that gap sat there for decades. Mathematicians kept nibbling at it, lowering the threshold, improving the bounds. But it wasn't until 2013, the same year Zhang Yitung made his breakthrough on prime gaps actually, which is a lovely coincidence, that the Peruvian mathematician Harold Helfgott finally closed the gap completely. Helfgott combined refined versions of Vinogradov's analytic methods with extensive computer verification of the smaller cases and proved the weak Goldbach conjecture outright. Every odd number greater than 5 is the sum of 3 primes. Full stop. No caveats. No sufficiently large. Just done. That was a genuine triumph. But notice, it's the weak version. 3 primes, not 2. The strong Goldbach conjecture, the original one, the one about every even number being the sum of just 2 primes, remains completely open. And the methods that worked for 3 primes don't seem to stretch to 2. It's as if you've proven that any odd width gap can be filled by 3 stones from your bag, but proving that any even width gap can be filled by exactly 2 stones requires a fundamentally different insight. There's another partial result worth mentioning, and it has a wonderful name. In 1930, a Norwegian mathematician named Viggo Brun, who had earlier done important work on twin primes actually, using sieve methods, inspired a whole school of thinking about these additive problems. And in 1966, the Chinese mathematician Chen Jinggrun proved something that gets tantalizingly close to Goldbach. Chen showed that every sufficiently large even number can be written as the sum of a prime, and a number that is either itself prime or the product of exactly 2 primes. Mathematicians write this as 1 plus 2, 1 prime plus a number with at most 2 prime factors. It's so close to the conjecture that you can almost taste it. you're allowed one prime and one almost prime, a number that's either prime or just barely composite. Chen's theorem is considered one of the finest achievements in analytic number theory, and the techniques he used, a sophisticated combination of sieve methods, pushed the boundaries of what those tools could accomplish. But almost isn't done. The gap between Chen's result and the full Goldbach conjecture is in some sense a single step. But that single step might require entirely new mathematics. It's one of those places where the last inch of a journey is harder than all the miles that came before. And here's something worth reflecting on. The Goldbach conjecture, the twin prime conjecture, the Riemann hypothesis, they're all, at some deep level, about the same thing. They're all asking, how do the primes really behave? Are they as well distributed, as cooperative, as well behaved as they seem to be? The Riemann hypothesis says the primes don't deviate too wildly from their expected density. The twin prime conjecture says primes keep occurring in close pairs forever. The Goldbach conjecture says primes are so abundant, so well spread among the integers, that you can always find two of them that add up to any even number you want. They're different facets of the same diamond, different ways of asking whether the primes are as generous and as orderly as all the evidence suggests. And in every case, the evidence is overwhelming. Trillions of zeros on the critical line, billions of twin prime pairs, quintillions of even numbers expressible as the sum of two primes. The patterns hold relentlessly without exception, but the proofs, the absolute, airtight, no exceptions ever proofs, remain elusive. Now, I want to shift gears a little, because we've been deep in number theory, deep in the world of primes, and there's a whole other landscape of unsolved problems that looks completely different. Problems that aren't about numbers at all, but about shapes, about space, about the geometry of the universe itself. And the most famous of these, the one that actually was solved spectacularly, in a way that tells you everything about what it means to work on these problems, involves a question about the shape of the universe that was first asked in 1904 by a French mathematician named Henri Poincaré. Poincaré was one of those figures who seemed to touch everything. He worked in celestial mechanics. He contributed to the theory of relativity before Einstein formalized it. He essentially invented the field of topology, the study of shapes and spaces and how they can be deformed without tearing. And topology is a strange, wonderful branch of mathematics. In topology, a coffee mug and a donut are the same thing, because you can smoothly deform one into the other. They both have exactly one hole. A sphere and a cube are the same thing, because you can round off the cube's corners without cutting anything. What matters in topology isn't angles or distances or sizes. It's the fundamental connectivity of a shape. How many holes does it have? Can you shrink any loop drawn on its surface down to a single point? That last question, about shrinking loops, is exactly what Poincaré asked, and his question, which became known as the Poincaré Conjecture, goes like this. Imagine you have a three-dimensional shape, mathematicians call it a three-manifold, that is closed, meaning it has no edges or boundaries, and simply connected, meaning any loop you draw on it can be continuously shrunk down to a single point without leaving the surface. Poincaré conjectured that any such shape must be topologically equivalent to a three-dimensional sphere. In other words, if a shape has no holes and no boundaries, it must essentially be a sphere, even if it's been stretched and squished and deformed beyond recognition. In 2 dimensions, this is actually pretty easy to see intuitively. If you have a smooth, closed surface where every loop can be contracted to a point, that surface has to be a sphere. It can't be a donut, because a loop going through the donut's hole can't be shrunk. But in 3 dimensions, things get vastly more complicated, because 3-dimensional spaces can twist and connect in ways that are impossible to visualize directly. And Poincaré himself couldn't prove his conjecture. He stated it almost as an afterthought, a question at the end of a paper, and then moved on to other things. He left it hanging there like a loose thread at the edge of a tapestry, and for nearly a century, some of the most brilliant minds in mathematics tried to pull that thread and couldn't. And here's what makes the Poincaré conjecture such a fascinating story. It's not just about the math, it's about the people. Because the road to solving it is littered with false proofs, broken careers, and one of the strangest acts of refusal in the history of human achievement. Let's start with what happened after Poincaré. For decades, topologists chipped away at the problem. They tried to prove it directly. They tried to find counterexamples. They tried to generalize it to higher dimensions. And something funny happened. They actually solved the harder versions first. In 1961, Stephen Smale proved the conjecture in dimensions 5 and higher. Think about that for a second. The version of the problem that seems like it should be more complicated, shapes in 5, 6, 7 dimensions, turned out to be easier to handle, because in higher dimensions you have more room to maneuver, more ways to wiggle things around and simplify them. Smale won the Fields Medal for this work, and it was a beautiful piece of mathematics. Then, in 1982, Michael Friedman proved the conjecture in 4 dimensions, which was significantly harder, and he also won a Fields Medal. So by the early 1980s, mathematicians had proven the Poincaré conjecture in every dimension except the one Poincaré actually asked about, dimension 3. The original question, the simplest sounding version, remained wide open. And the reason dimension 3 is so hard is a bit like why certain engineering problems are hardest at human scale. In very large-scale structural engineering, you can often ignore small imperfections. They average out. In very small-scale work, quantum effects give you different tools entirely. But at the middle scale, at the scale where we actually live and build things, you have to contend with every messy complication at once. 3-dimensional topology is like that. It's this sweet spot of complexity where you don't have enough room to use the tricks that work in higher dimensions, but the shapes are complex enough that you can't just see the answer. So the problem sat there, unsolved, through the 1980s and 1990s. And during this time, a quiet revolution was happening in geometry that would eventually crack it open. The key figure in this revolution was a mathematician named Richard Hamilton, working at Columbia University. Hamilton had an idea in 1982 that was genuinely radical. He proposed studying shapes not by looking at them statically, but by flowing them, by setting up an equation that would smoothly deform a shape over time, like heat spreading through a metal bar. He called it the Ricci flow, named after the Italian mathematician Gregorio Ricci Curbastro, who had developed the tensor calculus that Einstein later used for general relativity. Here's the intuition behind Ricci flow, and it's really beautiful. Imagine you have a lumpy, bumpy 3-dimensional shape, all kinds of irregular curvature, hills and valleys and weird protrusions. Hamilton's equation says, let the geometry evolve so that regions of high curvature spread out and regions of low curvature concentrate. It's exactly like heat flow. If you have a metal plate that's hot in some spots and cold in others, heat naturally flows from hot to cold until the temperature evens out. Ricci flow does the same thing with curvature. Over time, the shape should become more and more uniform, more and more regular. And if you started with a shape that's simply connected, no holes, remember? Then Hamilton hoped the Ricci flow would eventually smooth it out into a perfect sphere, which would prove Poincaré's conjecture. It's an incredibly elegant strategy. Instead of trying to prove directly that your shape is a sphere, you set up a process that gradually turns it into one, and then you just have to show the process works. Hamilton made enormous progress with this approach through the 1980s and 1990s. He proved it worked in many special cases. He built up a massive body of theory around Ricci flow, but he hit a wall, and the wall had a name: singularities. The problem is that Ricci flow doesn't always behave nicely. Sometimes, as the shape evolves, certain regions pinch off. Imagine a dumbbell shape, two round blobs connected by a thin neck. Under Ricci flow, that thin neck can collapse to a point in finite time, creating what mathematicians call a singularity. The curvature at that point goes to infinity, the equations blow up, and the flow just stops making sense. Hamilton knew about these singularities. He even had ideas about how to handle them. You could try to do surgery on the shape, cutting out the bad parts and capping them off, then restarting the flow. But making this rigorous, proving that you could always perform the surgery, that you'd only need to do it finitely many times, that the process would eventually terminate with a nice round sphere. That was extraordinarily difficult. Hamilton worked on it for years and couldn't quite get there. And then along came Grigori Perelman. Perelman is one of the most extraordinary figures in the history of mathematics, and his story is unlike anything else you'll encounter. He grew up in Leningrad, now St. Petersburg, in the Soviet Union. His mother was a mathematician, and his talent was apparent from a very young age. He won a perfect score at the International Mathematical Olympiad in 1982 when he was 16. He went on to do brilliant work in geometry, spending time at several American universities in the early 1990s, where he impressed everyone who worked with him. He was offered positions at Stanford, Princeton, multiple top departments. He turned them all down and went back to Russia, to a modest position at the Steklov Institute in St. Petersburg. And then he went quiet. For years, almost nobody heard from him. He stopped publishing, stopped attending conferences, seemed to have withdrawn from mathematics entirely. Some people wondered if he'd given up. But Perelman hadn't given up. He'd been working on the Poincaré Conjecture, alone, in near total isolation, for something like 8 years. In November 2002, Perelman posted the first of 3 papers to Archive, the online preprint server where mathematicians share work before formal publication. The papers were dense, terse, and contained almost no motivation or explanation, just the arguments, laid out with minimal commentary. The title of the first paper was about the entropy formula for Ricci flow. It didn't even mention the Poincaré conjecture, but mathematicians who read it carefully began to realize what Perelman had done. He had solved Hamilton's singularity problem. He had figured out exactly how to handle the pinching, how to perform the surgery, how to control the process so that it always terminated. His key insight involved something he called a non-collapsing theorem, a way to prove that the shape couldn't degenerate in certain catastrophic ways during the flow. He also introduced a quantity he called the W entropy, borrowing ideas from statistical mechanics and thermodynamics, showing that Ricci flow had a kind of thermodynamic structure that prevented certain kinds of bad behavior. It was a tour de force, drawing on differential geometry, partial differential equations, topology, and ideas from physics, all woven together with incredible technical power. But here's the thing. Perelman's papers were so compressed, so lacking in detail in places, that it took the mathematical community years to fully verify them. Several teams of mathematicians around the world, most notably Bruce Kleiner and John Lott at Michigan, and John Morgan and Gang Tian at Columbia and MIT, spent 2 to 3 years working through every line, filling in gaps, writing up complete proofs based on Perelman's outline. By 2006, the consensus was clear. Perelman's proof was correct. The Poincaré Conjecture was solved. And then things got strange. In 2006, Perelman was awarded the Fields Medal, the highest honor in mathematics, often called the Nobel Prize of Math. He declined it. He simply refused to accept it. The International Mathematical Union tried to persuade him. Colleagues tried to persuade him. He said no. He said he was not interested in recognition, that the prize was irrelevant, that if the proof was correct, that was all that mattered. Then, in 2010, the Clay Mathematics Institute awarded him the $1 million Millennium Prize for solving the Poincaré Conjecture. He refused that too. $1 million. He said he didn't want it. Reports from people who knew him suggested he felt the mathematical community had not treated Richard Hamilton fairly, that Hamilton had done the foundational work and deserved equal credit. Other reports suggested he had become deeply disillusioned with the ethics of the mathematical profession. He had reportedly been upset by what he perceived as attempts by other mathematicians to claim credit for parts of the proof. By this point, Perelman had resigned from the Steklov Institute. He was living with his mother in a small apartment in St. Petersburg, apparently unemployed, reportedly subsisting on her pension. He had cut off contact with almost all of his former colleagues. He told one journalist, "I have everything I want." It's one of the most remarkable stories in the history of ideas. A problem that stood for nearly 100 years, solved by a recluse who then walked away from fame, money, and his own career. And the mathematics itself, the way Ricci flow with surgery works, the way you can use differential equations to answer topological questions, has become one of the most powerful tools in modern geometry, influencing work far beyond the Poincaré Conjecture. So that's the Poincaré Conjecture, posed as a question in 1904, solved in 2003, the only Millennium Prize problem that's been resolved so far. And it gives you a sense of the timescales involved in these deepest mathematical questions. A century from question to answer. Generations of mathematicians spending their careers on partial progress that someone else would eventually complete. Now, let's shift gears a little. Because so far we've been talking about problems in number theory and topology, and there's a whole other family of unsolved problems that live in a completely different part of mathematics, the part that deals with computation, with algorithms, with the fundamental question of what computers can and cannot do efficiently. And the biggest open problem in that entire domain, maybe the biggest open problem in all of mathematics, is something you might have heard of even if you've never studied math at all. It's called P versus NP, and understanding what it really asks requires us to think about what it means for a problem to be easy or hard. Not for you personally, not in the sense of whether you find long division annoying, but in a precise, mathematical sense that has to do with how the difficulty of a problem scales as it gets bigger. So let's start there. Imagine I give you a list of 10 numbers and ask you to sort them from smallest to largest. Not hard, right? You could do it by hand in a minute or two. Now imagine I give you a list of 1,000 numbers. It takes longer, sure, But it's the same basic process, and a computer could knock it out almost instantly. 1,000,000 numbers? Still fine. 10 billion? A modern machine handles it without breaking a sweat. The point is, as the list gets bigger, the time it takes to sort it grows in a way that's manageable, roughly proportional to the size of the list times the logarithm of the size, if you're using a good algorithm. The key idea is that the growth is what mathematicians call polynomial. It doesn't explode. You double the input, and the work maybe quadruples or grows by some other power, but it doesn't suddenly become 1,000,000,000,000 times harder. Problems like this, problems where you can find the answer in polynomial time, belong to a class called PP for polynomial. These are the problems that computers can solve efficiently in a practical sense. Sorting, searching a database, finding the shortest path through a network, multiplying enormous numbers together, all of these live in P. Now here's where it gets interesting. There's another class of problems where checking an answer is easy, but finding the answer seems impossibly hard. And the classic example, the one that gets used in every textbook because it's so clean and intuitive, is the problem of factoring a number versus multiplying. If I tell you to multiply 7,919 by 6,271, you can do it. It's tedious by hand, but a computer does it in microseconds. The answer is 49,657,049, and you can verify that just by multiplying. But now, suppose I go the other direction. Suppose I give you the number 49,657,049 and say, find the two prime numbers that multiply to give this. Suddenly, it's a completely different kind of task. You'd have to try dividing by primes. 2, 3, 5, 7, 11, and on, until you found one that worked. For a number this size, it's manageable. But for a number with hundreds of digits, the best-known algorithms would take longer than the age of the universe on any existing computer. And yet, and this is the crucial point, if someone handed you the answer, if they said, the factors are these two 150-digit primes, you could verify it almost instantly. Just multiply them together and check. So, the problem of factoring is one where solutions are easy to verify, but apparently hard to find. Problems like this belong to a class called NP, and NP stands for non-deterministic polynomial time, which is a mouthful, but all it really means is, if you had a magic oracle that could guess the right answer on the first try, you could verify that guess in polynomial time. Now here's the thing. Every problem in P is automatically in NP, because if you can solve something quickly, you can certainly verify a solution quickly. But the question, the enormous, earth-shaking question, is whether the reverse is also true. Is every problem whose solutions can be quickly verified also a problem that can be quickly solved? In other words, does P equal NP? And if you're lying there thinking, well, obviously not, finding an answer is harder than checking one, then you're in good company, because almost every mathematician and computer scientist believes that P does not equal NP. It feels obvious. It feels like it must be true. But nobody can prove it. Nobody has been able to prove it for over 50 years. And the reason it's so hard to prove is that you'd have to show that no possible algorithm, not just every algorithm we've thought of so far, but every algorithm that could ever be conceived, fails to solve these problems efficiently. You'd have to rule out every conceivable shortcut, every clever trick, every approach that hasn't been invented yet. And that kind of impossibility result is extraordinarily difficult to establish. The formal framing of this question goes back to 1971, when a computer scientist named Stephen Cook published a landmark paper. Cook was working at the University of Toronto, and what he proved was something genuinely surprising. He showed that there's a particular problem in NP. It's called the Boolean satisfiability problem, or SAT, that has a special property. If you could solve SAT efficiently, you could solve every problem in NP efficiently. He proved that SAT is what's called NP complete. It's the hardest of the hard in a precise sense. Every other NP problem can be translated into an instance of SAT, so cracking SAT would crack them all. And almost simultaneously, a Soviet mathematician named Leonid Levin independently proved essentially the same result, though his work wasn't widely known in the West for years because of the Cold War divide. So the theorem is sometimes called the Cook-Levin theorem, and it's one of the foundational results in theoretical computer science. Now, what happened after Cook's paper is remarkable. Within just a few years, researchers started showing that all sorts of problems were NP complete. The traveling salesman problem, given a list of cities and distances between them. Find the shortest route that visits every city exactly once and returns home. That's NP complete. Graph coloring. Given a map, can you color the regions with only 3 colors so no 2 adjacent regions share a color? NP complete. Scheduling problems, packing problems, protein folding, circuit design. Hundreds and eventually thousands of problems from every corner of mathematics and computer science turned out to be NP complete. And they're all secretly the same problem, in a sense. If you could solve any one of them efficiently, you could solve all of them. They're all connected by these polynomial time reductions that Cook's framework made possible. Think about what that means. If someone, somewhere, found a fast algorithm for the traveling salesman problem, it would immediately give you fast algorithms for protein folding, for scheduling, for circuit optimization, for breaking most of the encryption that protects your bank account and your emails, and every secure communication on the internet. Because modern cryptography, RSA encryption, for instance, relies on the assumption that factoring large numbers is hard. If P equaled NP, that assumption would collapse. Every password, every encrypted message, every secure transaction would be vulnerable. The entire infrastructure of digital security is essentially a bet that P does not equal NP. So this isn't abstract. This is a question with staggering practical consequences, and it's one of the 7 Millennium Prize problems carrying a $1 million reward. But the money is almost beside the point. Resolving P versus NP would either confirm that there are fundamental limits to what computation can achieve efficiently, which is what most people believe, or it would reveal that we've been missing something profound about the nature of algorithms, that there are shortcuts hiding in the mathematical structure of these problems that nobody has found yet. And here's what's really fascinating about the state of play. Despite decades of effort by some of the most brilliant people in the world, we have almost no progress toward a proof either way. There are partial results, barrier results, proofs that certain techniques can't possibly work to resolve the question. In 1975, Theodore Baker, John Gill, and Robert Solovay showed that relativizing proofs, a broad class of arguments that had been the main tool in complexity theory, couldn't distinguish between P and NP. In the 1990s, Alexander Razborov and Stephen Rudich showed that another natural class of proof techniques, which they called natural proofs, also couldn't work, at least not without breaking cryptographic assumptions. So we don't just lack a proof. We know that many of the most obvious approaches to finding a proof are doomed from the start. Whatever technique eventually resolves P versus NP, it will have to be something genuinely new, something that doesn't fall into the categories of arguments we currently know how to make. That's a humbling situation. It's like knowing the treasure is buried somewhere in a vast field, and also knowing that your metal detector is fundamentally incapable of finding it. You need a completely different kind of tool, and you don't know what it looks like yet. But people keep working on it. Every year, a few papers appear claiming to have solved P versus NP, almost always claiming to have proved they're not equal. And so far, every single one has turned out to be flawed. It's become something of a running joke in the community, but it also speaks to the magnetic pull of the problem. People are drawn to it because it feels like it should be solvable, because the statement is so clean and simple, because the implications are so vast, and the question connects to something even deeper, something almost philosophical. It's really asking, is creativity fundamentally harder than verification? Is the act of discovering a proof, composing a symphony, designing a molecule, is that inherently more difficult than recognizing a good one when you see it? If P equals NP, then in some formal sense, the answer is no. Finding is no harder than checking. Every problem that can be appreciated can also be solved. And if P doesn't equal NP, then there's a permanent, provable gap between creation and recognition, between the search and the verification. That's a beautiful question, and it's wide open. Now, I want to stay in this territory of computation and logic for a moment, because P versus NP isn't the only deep question lurking here. There's another family of problems that connects computation to the physical world in a way that might surprise you, and it has to do with the equations that govern how fluids move. Water, air, the blood in your veins, the atmosphere swirling around the planet. These are the Navier-Stokes equations, and the question of whether they always behave themselves, whether they always produce smooth, well-defined solutions, is another one of those Millennium Prize problems. And to understand why a question about fluid dynamics ended up on the same list as the Riemann Hypothesis and P versus NP, we need to talk about what happens when you try to describe a moving fluid with mathematics. Because on the surface, it seems like it should be straightforward. You've got a fluid, let's say water flowing through a pipe or air rushing over a wing. At every point in that fluid, at every moment in time, there's a velocity. The water is moving in some direction at some speed. There's also pressure pushing on it, and there's viscosity, the internal friction of the fluid, the thickness of it, the way honey resists flowing compared to water. And all of these things interact. The pressure pushes the fluid around, the fluid's own motion carries it forward, and viscosity slows it down, smooths it out, dissipates energy. The Navier-Stokes equations are just Newton's second law, force equals mass times acceleration, applied to a continuous fluid. That's it, in principle. Claude-Louis Navier wrote down an early version in 1822, working in Paris, trying to understand how fluids behave in engineering contexts, canals, bridges, the practical stuff that mattered to a French civil engineer in the early 19th century. George Gabriel Stokes, working independently in Cambridge about 20 years later, refined the equations into their modern form. And what they produced is a system of partial differential equations that in principle tells you everything. If you know how the fluid is moving right now and you know what forces are acting on it, these equations should tell you exactly how it will move in the next instant, and the instant after that, and so on, forever into the future. Here's the thing, though. Knowing that the equations exist and knowing that they actually work, that they always produce a meaningful answer, those are very different things. And this is where the Millennium Prize problem lives. Let me try to make this concrete. Imagine you're stirring cream into coffee. You pour a little stream of cream in, and it starts swirling, folding, creating these beautiful tendrils and whirls. Now, in theory, The Navier-Stokes equations describe every single one of those tiny swirls, every tendril, every fold, every microscopic eddy. If you had perfect information about the initial conditions, exactly where every molecule of cream and coffee was, exactly how fast each one was moving, and you had infinite computational power, you could in principle solve the equations and predict exactly what pattern the cream would make. But here's what keeps mathematicians up at night. Can those equations ever break? Can you start with perfectly smooth, reasonable initial conditions? Nothing crazy, nothing infinite, just ordinary fluid doing ordinary things, and have the equations produce a solution that at some finite point in time just blows up? A point where the velocity becomes infinite, where the mathematics stops making sense, where the equations essentially crash like a computer hitting a divide by zero error. That's the Navier-Stokes existence and smoothness problem. In 3 dimensions, we don't know. We genuinely do not know whether solutions to these equations always exist and remain smooth for all time, or whether they can develop singularities, points of infinite velocity or infinite pressure, from perfectly well-behaved starting conditions. And you might think, well, surely in the real world, water doesn't suddenly develop infinite velocity. That's true. But the question isn't really about physical water. It's about the mathematical model. If the equations can blow up, it means our model of fluid dynamics is, in some deep sense, incomplete. It means the Navier-Stokes equations, which we use every single day to design aircraft, predict weather, model ocean currents, simulate blood flow, those equations might have a fundamental mathematical flaw. Not a practical one, necessarily, but a theoretical one. And that matters, because if we don't understand when and why the mathematics breaks down, we can't fully trust the model, and we can't know the limits of what it can tell us. Now, let me give you some context for why 3 dimensions is the hard part, because this is one of those cases where dimension really matters. In 2 dimensions, imagine fluid flowing in a perfectly flat sheet, like a thin film of water on a table. The problem is actually solved. Jean Leray, a brilliant French mathematician, did foundational work on the Navier-Stokes equations back in the 1930s. Leray proved that in 2 dimensions, solutions always exist and remain smooth. No blow-ups, no singularities, everything behaves. And the reason, roughly speaking, is that in 2 dimensions, there's a quantity called entropy. It's related to how much the fluid is spinning, that can't grow without bound. The viscosity always wins. It smooths things out faster than the nonlinear terms can roughen them up. But in 3 dimensions, that argument falls apart. In 3 dimensions, you get something called vortex stretching. Imagine a little tube of spinning fluid, like a tiny tornado. In 3 dimensions, that tube can get stretched, pulled longer and thinner by the surrounding flow. And as it stretches, it spins faster, the way an ice skater spins faster when they pull their arms in. This is a real physical phenomenon. It's part of how turbulence works. But mathematically, it means the spinning can intensify, and potentially, we don't know, intensify all the way to infinity in finite time. Vortex stretching is the mechanism that makes 3-dimensional fluid dynamics fundamentally harder than 2-dimensional. It's the thing that might allow singularities to form. Leray himself suspected that singularities might exist. He imagined what he called turbulent solutions. Solutions that start smooth but eventually develop some kind of catastrophic behavior. He couldn't prove they existed, and nobody since has been able to either. But he also couldn't prove they don't exist. And that's the state we're still in, nearly a century later. Think about what that means. We've been using these equations since the 1800s. They're the foundation of aerodynamics, meteorology, oceanography, cardiovascular medicine, chemical engineering. Every time you see a weather forecast, every time an engineer runs a computational fluid dynamics simulation to design a car or a turbine blade, they're solving some version of Navier-Stokes. And yet, we don't have a mathematical proof that the equations always make sense. Now, there have been partial results, and they're worth knowing about. Leray showed that something called weak solutions always exist. These are solutions that might not be perfectly smooth, but still satisfy the equations in an averaged sense. Think of it like a photograph that's slightly blurry. You can still see the overall picture, but some fine details are smudged. Weak solutions are like that. They capture the large-scale behavior of the fluid, but might not have well-defined values at every single point. The question is whether those weak solutions are actually smooth, whether the blurriness is real or just an artifact of our inability to prove otherwise. There's also a beautiful result by Caffarelli, Cohn, and Nirenberg from 1982 that says even if singularities do exist, they can't be too widespread. Specifically, the set of points in space-time where a singularity might occur has to have measure 0 in a very strong sense. It can't fill up a line, or even a curve. At most, it's a scattering of isolated points. So even in the worst case, the equations are almost always well-behaved. The potential blow-ups, if they exist at all, are vanishingly rare. But vanishingly rare isn't the same as non-existent, and the problem demands a definitive answer. There's something almost poetic about this. We can simulate fluids with extraordinary precision. Modern computers can model the airflow over an entire aircraft with millions of grid points, capturing turbulent eddies down to tiny scales. These simulations work. They match experiments. Engineers trust them with their lives, literally, when it comes to aircraft design. And yet, the mathematical foundations underneath all of that are not fully secure. It's like building a skyscraper on ground that you're pretty sure is solid, that has held up every building you've ever put on it, but you've never actually drilled down to check the bedrock. And this connects to turbulence, which is maybe the greatest unsolved problem in classical physics, period. Turbulence is what happens when fluid flow becomes chaotic, when smooth, orderly motion breaks down into a churning mess of eddies and vortices at every scale. You've seen it. Turn on a faucet slowly, and the water flows in a smooth, clear stream. That's laminar flow. Now turn it up all the way, and it becomes a noisy, chaotic splatter. That's turbulence. The transition between the two is one of the most important and least understood phenomena in all of physics. Richard Feynman called turbulence the most important unsolved problem of classical physics. Werner Heisenberg, yes, the quantum mechanics Heisenberg, supposedly said that when he died, he wanted to ask God two questions: why relativity and why turbulence? I really think, he reportedly said, he may have an answer to the first. Whether or not that quote is perfectly accurate, it captures the sentiment. Turbulence is hard. It's hard computationally, it's hard experimentally, and it's hard mathematically. The Navier-Stokes existence and smoothness problem is, in some sense, the mathematical doorway into turbulence. If we could prove that solutions always remain smooth, it would tell us something profound about the nature of turbulent flow. That no matter how wild and chaotic it gets, there's always an underlying mathematical order. And if solutions can blow up, it would mean that our equations for fluid motion are fundamentally incomplete. that there's some physics we're missing, some deeper description waiting to be found. So that's Navier-Stokes, a set of equations we've used for 2 centuries that work beautifully in practice, that we cannot fully justify in theory. A question about whether infinity can emerge from the finite, whether the mathematics of everyday fluids harbors hidden catastrophes. And there's a pattern here that I want you to notice, because it runs through so many of the problems we've been talking about tonight. The Riemann Hypothesis is about the hidden order in prime numbers, a pattern that seems to be there, that we can verify to extraordinary precision, but that we can't prove. Goldbach's conjecture is a statement so simple a child could understand it, verified for numbers up into the billions of billions, yet completely unproven. P versus NP asks whether finding is harder than checking, and we all feel in our bones that it is, but we can't prove that either. And now Navier-Stokes asks whether our most fundamental equations for fluid motion always work. And despite 200 years of evidence that they do, we can't prove it. There's something humbling about that. Mathematics is supposed to be the one domain where certainty is possible, where you can know things absolutely, where proof settles questions forever. And yet, here we are, surrounded by questions that resist proof, that hover in this twilight zone between overwhelming evidence and absolute knowledge. It makes you wonder about the nature of mathematical truth itself, whether some true statements are simply beyond our ability to prove, whether the architecture of mathematics has rooms we can see through the windows but never enter. And that question, whether there are true but unprovable statements, isn't just philosophical musing. It's actually a theorem. It was proven definitively by a quiet, meticulous logician in Vienna in 1931, and it shook the foundations of mathematics in a way that nobody saw coming. His name was Kurt Gödel, and what he discovered was something so profound, so unsettling, that even now, almost a century later, mathematicians and philosophers are still grappling with its implications. So let's talk about Gödel for a moment, because his story matters. And what he proved is one of the most remarkable intellectual achievements in human history. Kurt Gödel was born in 1906 in Brno, which was then part of the Austro-Hungarian Empire and is now in the Czech Republic. He was a sickly child, curious and intense, the kind of kid who asked questions that made adults uncomfortable. His family called him Herr Warum, Mr. Why. He moved to Vienna as a young man to study at the university, and he arrived at exactly the right moment in intellectual history, because mathematics was in the middle of a crisis, not a quiet, academic kind of crisis, a deep, existential one. Here's the background. In the late 19th and early 20th centuries, mathematicians had been trying to put all of mathematics on a perfectly rigorous foundation. The idea was to start with a small set of axioms, basic assumptions that everyone agrees on, and a set of logical rules for deriving new truths from those axioms, and then to show that every true mathematical statement could, in principle, be derived this way. No gaps, no ambiguity, no hand-waving. Just pure, mechanical logic, grinding out all of mathematical truth from a finite set of starting points. The most ambitious version of this program was championed by David Hilbert, who was probably the most influential mathematician of his era. In 1900, the same year he posed his famous list of 23 unsolved problems, Hilbert was already pushing this vision of mathematics as a complete, consistent, decidable formal system. Complete meaning every true statement can be proven. Consistent meaning, you can never prove a contradiction. Decidable meaning, there's a mechanical procedure to determine whether any given statement is true or false. Hilbert believed this was achievable. He famously declared, "We must know, we will know." It was an optimistic, almost triumphant vision of what mathematics could be. And then Gödel, at 25 years old, demolished it. In 1931, Gödel published a paper with one of the most understated titles in the history of science, On Formally Undecidable Propositions of Principia Mathematica and Related Systems. What he proved in essence was this: any formal system that is powerful enough to express basic arithmetic, and I mean really basic, just the natural numbers with addition and multiplication, any such system, if it is consistent, must contain true statements that cannot be proven within the system. Not statements that we haven't proven yet. Not statements that are too hard for us right now, but statements that are true, and that can never, ever be proven using the rules of the system. They are true, but unprovable. Forever. Think about what that means for a second. Hilbert wanted completeness. Every true statement provable. Gödel showed that completeness is impossible. There will always be truths that escape your net, no matter how carefully you weave it. And here's the thing. Gödel didn't just wave his hands and make a philosophical argument. He constructed an actual example. He built a specific mathematical statement within the system that essentially says, this statement cannot be proven. Now, if that reminds you of the old liar's paradox, this sentence is false, you're on the right track. But Gödel's version is far more subtle and far more devastating, because his statement doesn't say, this statement is false. It says, this statement is unprovable. And that's not a paradox at all. If the statement is true, then it's unprovable, which means the system is incomplete. If the statement is false, then it is provable, which means the system proved something false, which means it's inconsistent. So either way, you lose. Either your system is incomplete, there are truths it can't reach, or it's inconsistent. It proves falsehoods. You can't have both completeness and consistency. You have to choose, and since inconsistency is mathematical death, you're stuck with incompleteness. The technique Gödel used to pull this off was incredibly clever. He assigned numbers to every symbol, every formula, every proof in the formal system, a scheme now called Gödel numbering. This turned statements about mathematics into statements about numbers, which meant the system could talk about itself. He made arithmetic look in a mirror, and what it saw was its own limitations. Now, Gödel's first incompleteness theorem is the one I just described, the existence of true but unprovable statements. But he also proved a second incompleteness theorem, which is in some ways even more devastating. It says that a consistent formal system cannot prove its own consistency. So not only can't you prove everything that's true, you can't even prove that your system won't contradict itself. You have to take consistency on faith or prove it using some stronger system, which then has its own consistency problems. It's turtles all the way down. And I bring all of this up not just because it's fascinating in its own right, though it absolutely is, but because it connects directly to those unsolved problems we've been talking about all night. Remember that nagging feeling? The Riemann Hypothesis, verified for trillions of zeros, but unproven. Goldbach's Conjecture, checked up to astronomical numbers, but unproven. What if some of these problems are actually undecidable? What if they're true, but unprovable within our current mathematical frameworks? Now, I should be careful here, because this is a subtle point. Gödel's theorem doesn't say that any specific famous conjecture is undecidable. It says that undecidable statements exist. Whether a particular problem like the Riemann hypothesis happens to be one of them, that's a completely different question, and we don't know the answer. Some mathematicians have speculated about it. In fact, there's a fascinating argument that if the Riemann hypothesis were undecidable, it would actually have to be true, because if it were false, there would be a counterexample, a zero off the critical line, and you could verify that counterexample in finite time, which would constitute a disproof. So undecidability would imply truth, which is a strange and beautiful piece of logic to sit with. But the broader point is that Gödel revealed something fundamental about the landscape of mathematical truth. It's bigger than any formal system can capture. There will always be true things we can't prove. And that casts a long shadow over every unsolved problem, because you can never be entirely sure whether you're struggling with a problem because you haven't been clever enough yet, or because the problem is genuinely beyond the reach of proof. Gödel himself had a complicated later life. He moved to Princeton in 1940, fleeing the Nazis, and he became close friends with Albert Einstein. The two of them would walk together to and from the Institute for Advanced Study, talking about physics and logic and the nature of time. Einstein once said that in his later years, his own work didn't mean much to him, and that he came to the Institute mainly for the privilege of walking home with Gödel. Think about that. Einstein, arguably the most famous scientist who ever lived, saying the highlight of his day was talking to this quiet logician. But Gödel was also deeply troubled. He was paranoid, increasingly so as he aged. He became convinced that people were trying to poison him, and he would only eat food that his wife Adele prepared. When Adele was hospitalized in 1977, Gödel essentially stopped eating. He died in January 1978, weighing only about 65 pounds. The death certificate listed the cause as malnutrition and inanition due to personality disturbance. One of the greatest minds in human history, starved to death by his own fears. It's heartbreaking, and it's a reminder that intellectual brilliance doesn't protect you from suffering. But what Gödel left behind, that endures. His incompleteness theorems are as solid as anything in mathematics. They're not conjectures, not hypotheses. They're proven theorems, and they tell us something permanent about the limits of formal reasoning. Now, I want to take this thread and weave it together with something else, because there's a problem we haven't talked about yet that sits right at the intersection of number theory, computation, and this question of decidability. It's called the Collatz Conjecture, and it might be the simplest sounding unsolved problem in all of mathematics. Here's how it works. Pick any positive whole number. If it's even, divide it by 2. If it's odd, multiply it by 3 and add 1. Now take whatever number you get and do the same thing again. Keep going. The conjecture says that no matter what number you start with, you'll eventually reach 1. That's it. That's the whole problem. Let's try it. Start with 7. 7 is odd, so you multiply by 3 and add 1. That's 22. 22 is even, so divide by 2, 11. Odd, so 3 times 11 plus 1 is 34. Even, divide by 2, 17. Odd, 52. Even, 26. Even, 13. Odd, 40. Even, 20. Even, 10. Even, 5. Odd, 16. Even, 8. Even, 4. Even, 2. Even, 1. And there you are. It's been checked for every number up to about 2 to the 68th power. That's a number with more than 20 digits. Every single starting number eventually spirals down to 1. But nobody can prove it always happens. The great Paul Erdos said about the Collatz Conjecture that mathematics is not yet ready for such problems. And here's what's tantalizing. Some mathematicians have suggested that the Collatz Conjecture might actually be undecidable, that it might be one of those Gödelian truths that sits forever beyond the reach of proof. Geoffrey Ligarius, who has probably studied this problem more carefully than anyone alive, compiled an annotated bibliography of work on it that runs to hundreds of entries, and the honest conclusion is that we have almost no idea how to approach a proof. And there's something poetic about that, isn't there? The simplest possible rule, divide by 2 or multiply by 3 and add 1, generating behavior so complex that the entire apparatus of modern mathematics can't fully explain it. It's chaos hiding inside arithmetic. It's a reminder that complexity doesn't require complicated ingredients. Sometimes the simplest recipes produce the most bewildering results. Which brings me to something I've been wanting to talk about all night, a mathematician whose story is unlike any other in the history of the subject, someone whose work touched number theory, infinite series, continued fractions, and dozens of other areas, and who did it all with almost no formal training. I'm talking about Srinivasa Ramanujan, and if you've been waiting for his story, then here it is. Ramanujan was born on December 22nd, 1887, in a small town called Erode in the Madras Presidency of British India. His family was Brahmin but poor. His father worked as a clerk in a sari shop, earning maybe 20 rupees a month. They moved to the town of Kumbakonam when Ramanujan was still young, and that's where he grew up, in a modest house on Sarangapani Sanidhi Street. And even as a very small child, something was clearly different about him. He was asking questions about the distances between stars before he was 10. He was fascinated by infinite series, the idea that you could add up numbers forever and sometimes get a finite answer, before anyone had formally taught him what that meant. Now here's a detail that matters. When Ramanujan was about 15, a friend lent him a copy of a book called A Synopsis of Elementary Results in Pure and Applied Mathematics, written by a man named George Shoebridge Carr. This was not a great book. It was essentially a compendium, a list of about 5,000 mathematical formulas and results, most of them stated without proof. Carr had compiled it as a study aid for students preparing for the Cambridge Tripos exams. It was dry, it was dense, and it was decades out of date by the time Ramanujan got his hands on it. But for Ramanujan, it was a revelation. It was a catalog of mathematical truths, and he set about not just learning them, but deriving them, proving them for himself, and then going far, far beyond them. Working essentially alone, with no mentor, no university library, no mathematical community around him, he began filling notebooks with results, thousands of formulas, identities involving infinite series, continued fractions, integrals, partition functions. Many of them were known results that he had independently rediscovered, but many others were completely new, and some were so strange and beautiful that mathematicians are still trying to fully understand them today. And this is what makes Ramanujan's story so extraordinary, and honestly, so heartbreaking. He had this immense gift, but he was trapped by circumstances. He enrolled in college twice and failed out both times. Not because he couldn't do the work, but because he couldn't bring himself to study anything other than mathematics. He failed his English composition exam, his physiology exam. He simply couldn't be bothered with subjects that weren't mathematics. So he had no degree, no credentials, no position. He was working as a clerk in the Madras Port Trust, earning about 25 rupees a month, doing accounting work during the day and filling his notebooks with mathematics at night. Think about that for a second. One of the greatest mathematical minds in human history, sitting in a customs office, tallying shipping invoices. But Ramanujan was not entirely isolated. He had shown his notebooks to a few Indian mathematicians who recognized that there was something remarkable in them, even if they couldn't always follow the work. And in 1913, at the urging of some of these supporters, Ramanujan did something extraordinary. He wrote a letter to G.H. Hardy, a mathematician at Trinity College, Cambridge, who was arguably the leading number theorist in England at the time. The letter was about 10 pages long, and it contained roughly 120 mathematical results, stated without proof, in Ramanujan's characteristic style. Just the formulas, bare and unadorned. Hardy later said that when he first looked at the letter, he didn't know what to make of it. Some of the results were known. Some were wrong, or at least appeared to be. But some of them, and this is the part that changed everything, some of them were so deep, so unexpected, so far beyond anything Hardy had seen, that he knew they had to be the work of a mathematician of the highest caliber. He famously said that the formulas must be true, because if they were not true, no one would have had the imagination to invent them. He showed the letter to his colleague John Edenser Littlewood, and Littlewood agreed. They were looking at the work of a genius. And so Hardy wrote back, and he arranged for Ramanujan to come to Cambridge. This was not a simple thing. Ramanujan was a devout Hindu, and crossing the ocean was considered a violation of caste rules by his community. His mother initially opposed the journey, but eventually, in 1914, Ramanujan sailed for England. He was 26 years old. Now, what happened over the next 5 years is one of the most remarkable collaborations in the history of mathematics. Hardy and Ramanujan worked together intensely, and the results they produced were extraordinary. Their most famous joint work was on the partition function, the function that counts the number of ways a positive integer can be written as a sum of positive integers. So, for example, the number 4 can be partitioned 5 ways: 4, 3 plus 1, 2 plus 2, 2 plus 1 plus 1, and 1 plus 1 plus 1 plus 1. Simple enough for small numbers, but the partition function grows incredibly fast. The number 200 has approximately 3,900 billion partitions, and before Hardy and Ramanujan, there was no good way to calculate this for large numbers. What they developed was an exact formula. Well, technically, an asymptotic series that converges to the exact answer, using a method they called the circle method. It involved complex analysis, modular forms, and some genuinely ingenious estimation techniques. The formula they produced was one of the great achievements of analytic number theory, and the circle method itself became a fundamental tool that mathematicians have used ever since. Remember when we talked about Vinogradov's work on Goldbach's conjecture, proving that every sufficiently large odd number is the sum of 3 primes? He used the circle method, Hardy and Ramanujan's invention. But here's the thing about Ramanujan that set him apart from virtually every other mathematician who has ever lived. He thought differently. Hardy was a rigorous, proof-oriented mathematician in the finest European tradition. Ramanujan worked by intuition, by pattern recognition, by some process that even he couldn't fully explain. He would simply state results, often without proof, sometimes without even a clear indication of how he had arrived at them. When Hardy pressed him for proofs, Ramanujan could sometimes produce them, but other times he would say that the formulas had come to him in dreams, or that his family goddess, Navier, had revealed them to him. Hardy, who was a committed atheist, found this exasperating and fascinating in equal measure, and Ramanujan's results were not always correct. Some of his claims about the distribution of primes, for instance, were wrong because he didn't fully understand the subtleties of the Riemann zeta function and its zeros. those very zeros we talked about earlier tonight. He had worked out many properties of primes independently, but without knowledge of the critical line and the error terms that the Riemann hypothesis controls, some of his asymptotic estimates were off. Hardy helped him understand this, and Ramanujan absorbed the correction and moved on to even deeper work. But England was hard on Ramanujan in ways that had nothing to do with mathematics. He was vegetarian in a country that didn't understand vegetarianism. He was a brown man in an imperial society that was, let's be honest, deeply racist. He was lonely. Cambridge during the First World War was a grim, depleted place, and the English climate was brutal on someone from southern India. Ramanujan became ill, almost certainly with tuberculosis, though some recent researchers have suggested it may have been hepatic amoebiasis, a parasitic liver infection he could have contracted before leaving India. Whatever the cause, by 1917 he was seriously unwell, in and out of sanatoriums. There's a famous story from this period that captures something essential about who Ramanujan was. Hardy came to visit him in the hospital and mentioned that he had arrived in a taxi with the number 1729, which Hardy remarked seemed like a rather dull number. Ramanujan immediately replied that it was not dull at all. It was the smallest number expressible as the sum of 2 cubes in 2 different ways: 12 cubed plus 1 cubed, and 10 cubed plus 9 cubed. He just knew this. Lying in a hospital bed, wasting away from disease, and his mind was still doing that, still seeing patterns, still finding beauty in numbers. 1729 is now known as the Hardy-Ramanujan number, or a taxicab number, and the general problem of finding numbers expressible as the sum of 2 cubes in multiple ways remains an active area of research. Ramanujan returned to India in 1919, desperately ill. He continued working, filling one last notebook with results. This notebook, now called the Lost Notebook, was rediscovered in 1976 by the mathematician George Andrews in a box of papers at the Wren Library at Trinity College. It contained over 600 formulas, many of them dealing with what Ramanujan called Mach theta functions. And here's what's remarkable. It took mathematicians decades to understand what Mach theta functions actually were. It wasn't until the work of Saunders Zwegers in 2002, and then Ken Ono and others after him, that the theory was placed on rigorous footing. They turned out to be connected to modular forms, to the theory of black holes in string theory, to quantum gravity. Ramanujan, working alone and dying, had discovered mathematical objects whose significance wouldn't be understood for 80 years. He died on April 26, 1920. He was 32 years old. And I bring up Ramanujan here, at the end of our journey through unsolved problems, because his story illuminates something profound about mathematics itself. So many of the problems we've talked about tonight, the Riemann hypothesis, the distribution of primes, the behavior of partitions, the nature of infinite series, these were things Ramanujan touched. He didn't solve them, not in the way that a proof would solve them, but he saw into them. He produced formulas that encoded truths about these problems that we still don't fully understand. His work on the tau function and Ramanujan's conjecture, which was eventually proved by Pierre Deligne in 1973, as part of his proof of the Weil conjectures, connected number theory to algebraic geometry in ways nobody anticipated. His continued fraction identities have implications for the theory of modular forms that feed directly into the Langlands program. Arguably, the most ambitious unifying vision in modern mathematics, an attempt to connect number theory, geometry, and representation theory into a single coherent framework. And that's the thing about unsolved problems. They're not isolated puzzles sitting in separate boxes. They're connected. The Riemann hypothesis connects to the distribution of primes, which connects to the partition function, which connects to modular forms, which connects to the Langlands program, which connects to geometry and physics. The P versus NP question connects to cryptography, which connects to number theory, which connects right back to primes and the Riemann hypothesis. The Navier-Stokes problem connects to turbulence, which connects to weather prediction, which connects to the computational complexity of simulation, which brushes up against P versus NP. Gödel's incompleteness theorems hover over all of it, reminding us that some truths might be forever beyond proof. And maybe that's the most comforting thought to take with you as you drift off tonight. Mathematics is not a finished building. It's not a museum of solved problems with neat little plaques on the wall. It's a living, growing, sometimes bewildering landscape, and the unsolved problems are not failures. They're invitations. Every one of the problems we've talked about tonight is an open door. Someone, somewhere, maybe someone who hasn't been born yet, might walk through one of those doors and find something extraordinary on the other side. Think about Yitang Zhang, working in obscurity for years, and then suddenly proving that there are infinitely many pairs of primes within 70 million of each other. Think about Grigory Perelman, working alone in St. Petersburg, solving a problem that had defeated everyone for a century, and then simply walking away from all the recognition. Think about Ramanujan, filling notebooks in a house in Kumbakonam with formulas that the greatest mathematicians in the world couldn't fully understand. These stories tell us that mathematical discovery doesn't follow a schedule. It doesn't require prestige or funding, or the right university. It requires curiosity and stubbornness, and the willingness to sit with a problem for a very long time. And the problems themselves are patient. The Riemann hypothesis has been waiting since 1859. Goldbach's conjecture has been waiting since 1742. They'll still be there tomorrow, and next year, and next century. They're not going anywhere. And in the meantime, every attempt to solve them, even the failed attempts, generates new mathematics, new tools, new ways of thinking. The journey matters as much as the destination. So let that thought settle over you. The universe is full of patterns we haven't decoded yet. Numbers hold secrets we haven't uncovered. And the fact that we can even ask these questions, that a species of primates on a small rocky planet can wonder about the distribution of prime numbers and the nature of turbulence and the limits of proof itself, that's extraordinary. That's the real miracle, if you want to call it that. Not that we've solved so much, but that we can ask at all. Let your breathing slow down. Let the numbers fade. The primes are still out there, stretching off toward infinity, thinning out, but never stopping, hiding their pattern in the zeros of a function a German mathematician dreamed up over 160 years ago. The Collatz sequences are still spiraling, every one of them tumbling down to one through paths nobody can predict. Somewhere in the landscape of mathematics, there are truths waiting to be found, and some that might be waiting forever, true but unprovable, Gödelian ghosts in the machine. And that's okay. That's more than okay. It's beautiful. The incompleteness isn't a flaw. It's what makes mathematics infinite. There will always be another question, another problem, another door to open. And right now, you don't have to open any of them. You can just rest, knowing they're there, knowing the story goes on, knowing that tomorrow the primes will still be prime, and the patterns will still be waiting, and the great unsolved problems will still be sitting there, patient and eternal, like stars you can't quite reach but can always see. Good night.